we finish up with all the white papers, well, the white paper and the yellow paper, and I think it's time for us to conclude this series by taking a look at some of the details of that were mentioned in the yellow paper. So open questions that I had, mainly regarding the hash function and the way the data model is stored. Essentially the storage part of Ethereum. So I found a very good explanation in one of the Ethereum Stack Exchange questions. So I recommend first recommend this website, and specifically this particular question that you have the link on the screen. So somebody asked for a diagram and give an example. This diagram is it's an example of what he would like to know, but it refers pretty well to the Bitcoin diagram. So in the Bitcoin block header, you do have this information: the previous hash, the nonce, and the Merkle root, which points to which is the Merkle root hash of the Merkle tree, containing all the transactions hashed. Right, so that's actually quite relevant. In the case of Ethereum, this is quite more complicated. Right? So this is a very good drawing diagram of the model of Ethereum. So we will go through that. Before that, let's take a look at the Patricia Merkle Tree that's used in many places. So there are three trees like this in Ethereum: one for the state, one for the logs, and one for the receipts. So to remind you what it is, the state is the storage. The account storage is stored as a tree. So this type of tree. The receipts is when you make a transaction, you get a receipt for the so that you can prove that it has been executed. A node can prove that it has been executed. And the logs is basically, since transactions are synchronous, your program can emit a log record whenever some important event has been done. For example, we had a liquidity pool creation function, and when you call that function, you will not know that the pool is created because it will be created asynchronously. The transaction will return with simply a hash, and then the function will be invoked, and the pool will be created. When that happens, that function will emit that log, like a signal if you prefer. So these three data structures are stored in Ethereum as a Patricia tree, as a Merkle Patricia tree. So how does it really look like? So we know that this kind of tree maps a key to a value. So remember, the storage is basically a key value pair. So in Ethereum, the values are can be arbitrary. They can be complex data structures, meaning that they can have strings, they can have integers, they can have value, like floating value, so on and so forth. But since everything can be translated to binary with the RLP format, serialization format, we can assume that the value is just in this diagram, the value is simply the amount of balance in this account. So we want to store, this diagram stores these accounts. For simplicity, the full account number is not shown, but just the 7 first digits, and the value is simply the account balance. So normally you would have way more behind, and then we will see what we would have exactly in the other diagram. So let's suppose that you want to store this. So this tree, this is an index tree, and it works actually very similarly to a dictionary. So if in a dictionary you would have a letter, an index, which allows you to jump directly to the part of the dictionary that begins with that particular letter. So if you imagine that that this alphabet has only 16 letters, because it's hexadecimal, so it's 0 to 9 and A to F, so it's only 16 possible symbols. You would have 16 index entries here. So every node has at least 16 slots here when it's branching towards something smaller. And so let's also say that there are three different kinds of nodes. So we have branch nodes, we have extension nodes, and we have leaf nodes. So the main ones are branch and leaves. The extension is kind of like optimization over having just branches and leaves. So we need to take a look at the branches first. So you can see that the branch is basically one entry per letter or symbol, and then you will branch to that particular part of the dictionary if you want, which begins with that symbol. So in a real dictionary, you would have A to Z, and you would have all the words in the A section under that index A. So you would follow the index A, and by flipping to that page, you will get to the first word that begins with A. But let's imagine now that your dictionary that has so many words that you need going to that A is not enough, and you want to have that A entry indexed even further. So you could imagine that going to that section A is actually going to another book which only contains the A's. Like it's no longer a simple dictionary, but it's more like an encyclopedia. And then in the A's, you would again have another index, again from A to Z, which lets you jump further down. So, for example, if your word is A7, then you will go to the book A. We have 26 books, but in our case, we only have 16, right? We go to that book, open it, and then we have to jump. We have entries for, again, 0 to 9 and A to F. So we can look at the entry for 7, and so on and so forth, right? So we know that eventually, since the keys is a fixed length, we will get to the keys is a hash, right, for count hashes. So we know that after a certain number of digits and letters, or levels if you prefer, you will get to the end, and then you will have a value. So simply the end, the leaf node, is the end of the tree. So all the way down, you will find finally you will find a single word, and then that word would have the value associated, right? So that would be the way you store on these values in a tree if it was a normal index tree, radix tree. But in the case of a Patricia tree, it's we want to store prefixes. So the reason why we want to do that is that these guys are hashes, so they will be distributed very randomly, and very quickly you will get to a point where everything will be a single option. So basically, after let's say 10 levels, there will be only one hash that actually has this exact beginning. So then you will have a branch node that only has one entry, for example 7, to go to another branch node that only has one entry. Then you have to follow 3, and so on and so forth, all the way to the end. So that kind of tree will be looking more like a linked list, like a list of nodes linked together, rather than branches. So this is like if you look at a tree, and suddenly instead of having a trunk and branches diverge from the main branch, you actually have one really long branch that continues. And storing all these values from 0 to f, all these entries here, having slots that are all empty except one, it's not efficient at all. And this is going to happen quite a lot because we are using hashes. So what we would prefer to do is to notice that if there is only one single option for a particular path, or subpath, should I say, we are going to store that portion in the extension node. Right. So let's look at this guy, for example. We'll look at extension node first one. We see that it has A7 as a share nibble. By the way, a nibble is this letter. So if you only have 0 to F, 16 letter digits, you're talking about hexadecimal, a byte is encoded in 2 of these symbols. So this is actually 1 byte, this is 1 byte, this is 1 byte, and so on and so forth, right? And a nibble is simply half of that. So something that goes between 0 and 15. So we notice here that all these guys, all these keys, they begin with A7. So there's no need for us to go to the to have a branch node that has only A set, that refers to a next branch node that only has 7 set, right? So we can optimize this by saying that, hey, if your entry is not A7, you might as well leave, because this is all we have below. So we have A7 that allows us to skip 2 branch nodes and have these nibbles simply store there. Right? So that means that if you are following A7 something, then you're good. You follow from here. If you're not getting A7, then your entry is not in the tree. Your key is not in the tree. And so we follow A7, we get here, and then we see that there's an entry for the slot 1 is occupied, the slot 7 is occupied, and the slot F is occupied. So that tells you that, oh yeah, 1, 7, F, and 7. So these are the only 3 options. 7 is repeated. Right? So anything else, again, is not going to be one of our keys. So all the other values here, all the other slots here are going to be empty. So if by chance, or if we're looking for something that begins with 1, then this is the only option we have in this particular set of records we want to store, right? You can see that nothing else has a 1 in the 3rd position. So that means that we reach the end of the tree, and then we want to get the value. So if we have 1, so now we have A71, so we follow this path, right? So we need to record what are the nibbles we use so far. So we use A7 from the extension root, then we use the 1 from the branch, and now we need to know also the remaining. So the leaf itself has the remaining part, and the remaining part is 1, 3, 5, 5. So the entire path is A7, 1, 1, 3, 5, 5. 1, 7, 1, 1, 3, 5, 5. And you see it matches that key. So because it's a leaf node, then we can read the value 45. So you may notice this particular prefix here, right? And we come to that later. So extension nodes and leaf nodes have this prefix. But this is not important for the construction of the path. So let's see what happens if we're not getting, if we are following the 7 instead. So if you follow 7, we know that it's because the key begins with A77. And here we reach an extension node, which works exactly the same way as this one. So that means that after A77, there is no other option than having D3. Anything else will not be in the tree. So now the path becomes A7, 7, D3, and we have a branch node. So we have several sub-options. And the sub-options is 3 and 9. So we should have something that has A7, D3, 3, and A7, D3, 9. So let's take a look. E7, 7, D3, 3, A7, 7, D3, 9. So these are the two entries, the second one and the fourth one, which are present in our data set. Right? And after that, we are reaching the leaf because we only have one option of each. But these options have some remaining part of the key. So they both happen to have 7 at the end. Right? And then there's another case, right, where after your branch, you have a leaf node. So if you have A7F, then the only option would be 9365. A7F 9365. So that's how you store. That's how this stuff is stored, right? So let's store. That's how this stuff is organized. This is how Patricia tree is organized. So there are algorithms, of course, for changing the values, adding new key values, and deleting them. But this goes beyond the scope of this little overview. Let's just say that this is not as simple as it is, because you will have to do some tree reorganization. So one simple thing to notice is that, for example, if you insert something that begins with A but not 7, but let's say A1, then suddenly this doesn't work anymore, right? Because you would have you should have a branch node now, right? So you should begin with a share level, so an extension node, because the prefix there's still a common prefix, which is A, but 7 is no longer common. So you would have a branch node that has 1 and 7 in that case, and some rebalancing would happen afterwards. So the only thing that is relatively simple is changing the value, because then you just go down, find the node that represents the key, and change the value. This doesn't change the structure of the tree. But if you insert a key, or you change or you delete a key, changing a key itself is done by deletion and insertion. You don't change the key explicitly. So you can change the value, but if you want to change the key, you have to delete the node and insert a new one. So the three operations you can do is insertion, deletion, and changing the value. Changing the value is relatively simple, but inserting and deleting may change the structure, right? If you delete a node, then you could have a better compaction, in a sense, because some of the nodes could be shared, and you could replace them with an extension node. Okay, so the only thing we have to cover now is the prefix. So we said that extension node and leaf nodes have this little prefix. So there are two reasons. So you can see that these guys only have 4 different values, right? One of them is simple. So you can imagine that actually there are 4 values, but it's because there are 2 options, and those options are independent. So imagine it's like 2 switches, switch A and switch B. You can have both of them off, one of them on, first one on, second one on, and both of them on. So you have 4 different options, right? Both off, both on, one on, and either one wrong, right? So one of the switches, one of the indicator, is whether you have an even or odd number of these nibbles. And the reason being that, see here you have 1, 3, 5, 5, right? But here you only have 7, so only an odd number of nibbles. The reason being that when you store things in practice, when you store things in that tree, you have to work with bytes. You cannot work with half a byte. The smallest unit in computers will be bytes, right? So when you store a 7, or when you store anything that has an odd number of nibbles, you're gonna have to put a 0 in front. So this is called padding. You have to pad to an even number of nibbles, because you need to have bytes. So there will be no way to distinguish between 07, the real 07, and 7 because it's odd. So therefore we need that little indicator, and that will be one of the switches. So when you see that the number of nibbles is even, like there are 2 here, 2 here, and 4 here, then the prefix will be also even. So 0 or 2, right? And when it's odd, it's going to be odd as well. So it will be either 1 or 3. And the second switch is simply to indicate the type of node, right? So every node that is an extension node will have a prefix of 0, right? Otherwise you have 0 here, right? And then it's a prefix here, 0, and when it's a leaf, it's going to be the other switch, right? So another way to know that it's a leaf is to see if the prefix is greater or equal to 2, right? So one is the whether nibble length is even or odd. So that will also give you a prefix that is even or odd. And the second one is whether it's an extension node, the prefix will be lower than 2. And if it's a leaf node, the prefix will be greater or equal to 2. Right. So that put together, right? So you take the prefix, right? So why do we need that stuff, right? Because you could say, well, extension node and leaf nodes, they look different, right? Well, once it's turned into bytes, it's not very different, because how it's stored is that the prefix and the share nibble is put together to form actual key as well, right? So you need to store this stuff in the database, right? This is not that these links would be possible to store. We don't store the diagram, right? So in the database, what we do is that this becomes a key, and when you have a next node, right? So this is, for example, pointing to the next node, pointing to the node here, pointing to the node here. So this guy here should contain a way to find this node. Whenever you have a link like this, this is expressed as how there must be a way to go from whatever value is here to actually get that content here. And this is a Merkle tree because all of these links are expressed by hashes. Okay, so what I mean by that is that if you have this leaf node, then you hash it. You do this Tirsac 256. You have a hash, and that hash is what you will put in the branch node. Right? And then if you have then you will have a hash here and a hash here. Right? This is a hash of these nodes, right? Nothing to do with these guys. So you have a hash here and a hash here, and there's nothing elsewhere. And this whole thing, this whole branch node, then is also hashed to get the hash that is here, right? And then this whole thing is also hashed to get this one, and so on and so forth, all the way up to the top, which gives you the root hash, the root hash. Then you can see why the structure is very similar to a Merkle tree, right? The Merkle tree, we were hashing 2 guys together. So here we are hashing all these children entries together. But that's the same idea, which means that if you have a value that changes, for example, this guy changes to 15, 015, this hash changes here, the leaf node hash changes, which changes the value that's recorded in the branch node, which therefore changes the hash of the branch node itself, which changes the value that's recorded here, which changes the hash of this extension node, and so on and so forth all the way to the top. So changing this value here will change the hash that you have up there, right? The hash of the root node, right? And likewise, if you want to prove that nobody tampered with this guy, well, you can reconstruct the path, right? So you know that I'm giving 012 and I want to prove to you that 012 is the real value of that particular leaf, right? So in our word, I want to know the account balance of A77D397, right? So I don't have this tree, and we will see that some clients actually do not have this data at all, right? But I want to know the balance of this particular account. So I'm going to ask another node for this particular account value, and the node could give me this. Like, you give me the answer is 12 Ether, but there's no reason for me to believe it, right? So like we ask for a Merkle proof, we can ask for a Patricia Merkle proof, which means that hey, the node will give us not only that value, but this node, right, with the prefix and the key and everything. Also this branch guy, right? So everything that led to there. So it has to give us quite a bit more, right, than this value. So it has to give us this guy, or every node that is on the way to that node, to the leaf, and that would be enough, right? Because there's no way for anybody to actually be able to generate all this data without having it to hash to something else at the top. Because if you change anything in these nodes here, then you will not get the same root hash that is actually included in the block header. So assuming, of course, that the client, that whoever requests this data has the block header, he can verify that proof. Okay, so that's the Patricia Merkle tree. Another important notion is actually how this tree fits in the rest of the picture. So we have quite because it's a bit of a complex picture, but we can analyze it little by little, right? So this represents what the miner has, right? And the miners have a bit more work to do than a regular node. But let's take a look, right? So first job it has to do when it wants to mine a block, right, is that it would take a bunch of transactions, and so remember also that transactions are also floating in the network. So you're sending transactions to other peers, to other nodes, and they distribute that transaction through the protocol, like a gossip protocol. They call it Whisper, I think. But the miner is able to choose which transactions to include, and that has to do with the fees. Right? You would try to maximize the benefit by, for example, picking transactions that give him a big reward, a big fee. Like, for example, high gas price multiplied by gas usage, something like that, right? And if there are too many transactions to put in the block, then it also finds the omers. So remember that because of the blocks are created very quickly, you could have blocks that were found by other miners, but they do not end up being in the main chain, right? So if you have omers, that then you can include them and get and they will get some reward, right? So if you are a miner and you had blocks that unfortunately you mined but were not successful, then you can add them. Then you calculate the reward for yourself, right? So now the big stuff, right? So the big stuff here is about how you calculate the new state, and we can take a look at that guy. So you have a set of transactions, right? And you have to apply each transaction one by one. So this is the gamma applied to this. The sigma t is the current state, and all it says here is that knowing the current state and the transaction, this apply function, called gamma, will compute the new state. And this goes for this particular loop, right? So the loop says that you take the next instruction. So this is normally it's a sequential program. You have a bunch of instructions, and then you execute them in terms, right? So based on the instruction, you know if you have entries to add or remove on the stack, right? For example, there will be instruction that says push this number on the stack. There's an instruction that says sum the two numbers that are on top of the stack and leave the result on the stack. So each instruction will indicate how many entries it has to remove and add on the stack, right? Then you do that. Then you subtract you spend some gas, so the gas usage is deducted, and you go to the next instruction, right? So sometimes in the next instruction, it's actually going to tell you, okay, go back and change back to the. So this is how you would do a loop, or the instruction will say, if the content of the stack, if the value on top of the stack is 0, then jump, otherwise continue. So you also have conditional jumps. But only these things. You have also instruction that would say, take the content of storage at address blah 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 at key blah blah blah, and put the result on the stack. Right. So having all these instructions will be enough to implement this Turing machine. Right. There's a bunch of other. So this is all the instructions. Right. So this is not actually your program, because your program. No, I think it is actually your program. So what they say here is that first instruction, so instruction at counter 0, index 0, is stop. So this program is not going to go very far, but it's an example. And then you have add melt, right? So this is your program, right? And then your execution environment is the mini bunch of data that you want to keep in order to run this program. So this is like your scratch space, right? If you are a machine and you want to execute this stuff, right? You want to know before you start what is the parameters, right? So that is basically your context, right? So what do you have? Well, you have whoever creates that code, who sent the transaction, how much is the gas price, the data that was sent with the transaction. So causer is if it's nested, right? So this is the account that calls you, and this is the account that has created the code. Okay, so that's a bit bigger now, right? Okay, so there's a value that's passed to the transaction, right? So how much is basically, if you spend, it would be how much you would spend, but or how much you can send to the contract. The code actually of the contract that has to be executed, the header, the current block header, and also this is how nested you are in the call graph. So if you call something that calls something that calls something, this guy increment, because there's a limit on how deep the function can be executed. So after a particular number, the machine will refuse to create more entries, go deeper than that. So this actually is the input to that particular execution of your code here, and this is the logic that executed line by line, right? So you can imagine, you can consider this as the starting point, because each code, right, even though it's the same code, can be interpreted in a different context. All right. So as the virtual machine executes your code, it will keep in its own memory, in its own scratch space, these values. So the gas available starts with the gas that you are willing to spend, right? So that will be computed in the beginning by saying that there's a gas limit, and then it would be decremented every time you run an instruction. So the program counter would start at 0 and then be normally incremented every time we do instruction. The memory content is the memory that we have allocated to this program. Note that the storage is not there, because storage is not going to be transient, right? Storage is going to be is permanent. So we only have stuff that will be wiped out at the end of execution. Active number of words in memory. So this this is just the I think, right? This is the size of this entry, right? Because memory is supposedly infinite, right? And you can allocate, but then you keep track of how long this array is, and then you have the stack. And then whenever you go to a function, you also create a substate. So substate is the state that could be reverted, right? If everything goes well, this will be written. So actually, this part, I think we skipped in the yellow paper. Okay, so we can see what it is, right? So the suicide set. So if the transaction, if you have like commit suicide, that means destroy yourself, self-destruct. If the transaction succeed, then all these guys will be destroyed, right? And these guys are the log records are created. If the transaction succeeds, you will emit them. And then refund balance, price of gas, the transaction. Yeah, so this is just the values, right? And you keep that because as this program executes, these sets will change, but it will only be committed if the transaction succeeds. So the definition of the substate is section 6.1 of the yellow paper. It's quite short, actually. I missed it and I read it the first time. Okay, so there's a thing about the proof of work, right? Then the principle of proof of work is that you change the nonce and you recalculate the proof of work and you figure out if it's lower than the target value here. So the higher the difficulty, right, the lower this number will be, and the harder it will be to have a proof of work that is lower than this bound, that is upper bound. So difficulty therefore increases division. It's exponentially. We kind of talk a little bit more about this POW because one of the questions I had was around how the Ethash is calculated, and Ethash is part of the proof of work. But let's go now to the right side. Okay, so the first part of the right side. So the first part, the upper part of the right side is a visual representation of the blockchain, right? So each block is linked to the next one through the parent hash. But hard to read here, and it's getting bigger and bigger. So you can see here that it's linked through the parent hash. So the block header is hashed, and the result has to be put in the next block. Right. So what do we have here? Right? We have, okay. So this one, the biggest one, is the easiest to read. We have the Homer's hash, which are the ones like that are of they share a common ancestor, but they are not in the direct path. So sometimes they are called uncles, but this is not necessarily an uncle because it could be further up, and Ethereum accepts 7 levels up. Right. And for our uncle, the block hash, the block is included. No, the block header is included, but the content is not included. So you just need to prove that you have hashed something, but you don't have to provide the transactions and the state, right? And you will get a reward for that. Then beneficiary is the address of usually the address of the miner, because he's the guy who's going to receive the reward. The state root is this big thing here, so we'll take a look at that. Transaction root is also the root of the tree that contains the transaction. So this is all about like Merkle Patricia trees that we just saw, right? So whatever you put in the Merkle Patricia tree as values doesn't really change anything about the construction of the tree. We didn't, when we look at that tree, we didn't really pay much attention to the values. So it was all about like how the keys are organized. So we can store transactions, state, and receipts in the same way. Now we have a logs bloom. So the logs bloom is a bloom filter, which allows you to find easily if you have a particular log entry. So you can go and see what the bloom filter is. It's not as complicated as the name implies. It's actually just a set of bits which is set if a particular entry is present. So it's a bit field that indicates absence or presence of a particular key, right? But there's collisions are unavoidable because we want to keep the bloom filter fast. So it's more like a quick way to see if that entry is not there, right? Because if it's not there, you're gonna have 0. The bit will not be set. But if it is there, it's gonna be set. 0 is not there. But if it's 1, the bit is set. It may still be not there. That's what it means. So difficulty store number is a block number. Gas limit is the total gas limit. Gas use is the total gas used on the block. Timestamp. Extra data, something you can add. Mix hash. So mix hash has to do with the Ethash. So these guys together. So this guy you can change, and this is the proof that you have actually taken a look at the set. So this and this is for the proof of work, and we'll talk about this later. Right. Now the only things that we have to talk about is so we know the transaction tree is Patricia tree of transactions. The transaction receipt tree is the same with the receipts. And the transaction receipt has the state after the transaction, and this is to show that you have executed the transaction. Gas use, logs, and bloom filter, right? So that should be fine, because this is basically the same as what you have in the block, but relatively to that particular transaction. So if we know each of these entries, what they mean, right? And for each log, because you have a transaction log here, you have the guy who logs the address. So remember, a log is any message that you want to emit. Right? You can say emit hello, for example, right? So whoever emit a message, the topic would be, for example, greetings, and then the data would be hello. Then so the only thing we have, we have transaction. So transaction, we have seen so many times, but it's worth seeing again. There's a nonce, which is the nonce of the same nonce as the account nonce that has sent the transaction. Gas price, gas limit, where the transaction is sent to, the value on the transaction. And we have init or data. So init, if it's the first call for the creation, and init will be the values are part of the so you have the code, actually, of course, of the contract, but you have also parameters that are sent to the constructor, right? And if it's actually a normal call, then you will have the input data, and basically it tells you which function to call and which are the arguments to that function, and then this is the signature. Okay, and finally the account storage. So account storage, so this is the part where we didn't exactly know, right? Is that the storage is per account, and the storage is actually stored as a Patricia tree, right? So each account has its dedicated storage, and that storage is stored as Patricia key, right, as well as the transaction tree and receipt tree. And then the root is put into that account information. So nonce is because we have to verify that the account nonce is the same as the transaction nonce if this account emits a transaction. So we have to keep track of that. We have to keep track of the balance, and we have to keep track of that storage root, and we keep track of the hash of the code if it's a code contract. So this is for optimization, right? It can't change. Once you create the code, you cannot change the code. And all this stuff together represents the data that is associated with an account. And that data itself is a value that is also put into a Patricia tree, which is now called the world state tree. And that's the famous sigma that transactions can change. Right. So here you have it. If you are an account, then the machine would do is it would go through the world state tree, find your account, so it would navigate down the tree to look for your account data, right? Then once it finds your account data, it will be this stuff. Right? If it needs the access storage, then it would go through the storage tree and get to your particular value that you have stored, right? And that would be all the information for your account. So I think that these three here and these trees here are not kept by the nodes. They only keep that. And that also depends on which kind of node you have. This is required because you want to verify. You want to verify that the transactions are. If you ask for a current node, you can ask for what was the transaction number 25, right? And then you can have a proof that from a node that has it, whether it's correct or not. So let's talk about what kind of node you have, right? You can have a node that contains everything. So you also see that state changes all the time, right? Whenever you execute a code, world state will change, and the way they change it is that when you change for example, a value in the storage, you will get another hash here, and then that hash will imply a new hash in the parent. So all these little boxes, right, are actually stored in the database, in the real database, a key value database, which has keys or hashes, and values are the content of these boxes, right? So let's say you change this, right? Then you will get a new value. Therefore, the box will be different, so you will have a new hash, and then you will create a new entry in that database, mapping that particular hash to that particular new box value. Right? So if you just do that, right, you actually didn't remove the old one, right? And the kind of the beauty of that is that if you have, if you know the history, right, you have the state root of block number 1, and you have been doing this without deleting anything, then you can you can go from that particular state root, navigate as if you were navigating normally, and you will have the state of Ethereum at that point. So this is like a time machine. You have everything, right? Of course, the drawback is that this takes an enormous amount of memory of this space, right? The state root that was reachable at that point, most of the stuff may not be reachable anymore. Right? So nodes will not keep all of that. I think that if you do now, and you are running in that particular fashion, your archive node, and archive node will require more than 4 terabytes of disk storage at this point. So there are very few, if not any, archive nodes running, because we're talking about 4 terabytes of data that it probably has to be on a SSD. The way this is stored in a database, because everything is a hash as a key, and the value is fairly small, right? It's very inefficient for a database. There is no optimization that the database can make that would make storage of this data fast and compact. So you still need fast, because this is going to be navigated like a lot in order to get to a particular value. You will have to go through several nodes and perform several lookups in that storage, in that database. So it has to be very fast, and it keeps being changed. So new nodes are created. Every time you change a single value here, you're gonna create another entire entry here, and you're gonna impact all the paths to the node, to the root. So all these intermediate nodes would have to be created as well, because they get new hashes. So the impact of activity is very high, and if you do that with on a hard drive, on a mechanical hard drive, you would not catch up. So you need 4 terabytes of SSD, and that's obviously very expensive. So I don't think there are too many of these nodes. Then the second type of node is the full node. Full node do keep the state, but they keep the current state, plus potentially a few state back, right? So maybe like 10, 20, it's like 64 actually, I don't know. So a certain number of past state. Then you have, and the way they store the past state could be different. It could be like as deltas, as just a difference, or they can store the full state really as these nodes are going to be there in the database. But they have to have some way of pruning the tree. Right? The many portion of the trees that would be unreachable by the new root node, because the state keeps changing. So you can prune, you can remove these unreachable entries, and essentially only keep the latest version. But that's still pretty large, right? And then you have the final type, which is the light node. The light node kind of cheat, and they pretend that they have this data, but they only have the block headers. And what they do is, if when you execute a particular function, they can't verify anything, right? Because they don't have the state. But if you are trying to execute a function on your node, and that node, so you execute a function, you want to submit a transaction, so the transaction will be verified before it's broadcast, right? It will query peers on the fly and ask them for the content that they don't have. They may cache the result in their own database, but since in the beginning they have nothing, every time there's a value that is requested, they will go ask a peer. So without other full nodes participating, the light nodes cannot do anything. But other than that, if they have this support, then they will have the ability to function as normal. So if you take a light node, you can sync up a node, install a light node in a matter of minutes. I think that definitely less than an hour. But if you go full node, it's going to take you, I think now more than a week. And you need a SSD as well, because that state, even the current state, mutates too fast to be on a mechanical hard drive. So I think the requirements now is at least like 4 to 8 gig of RAM, and for 500 gigabyte of SSD. Okay, so that's actually should cover the Ethereum model machine, and then now we have the last thing we wanted to talk about is this proof of work, right? So it's more like for curiosity than anything else. But proof of work, we mentions, this is the same drawing here. We have done this one. Yeah, so this is proof of work, and why they have done special work on this is because they want to avoid that. They want to avoid these farms where this is a Bitcoin farm of computers that are essentially calculating Bitcoin hashes all the time in order to find the nonce and claim the reward. So this kind of investment is not possible for the enthusiast. So it is more like a business doing this, and that means that the mining has been concentrated quite significantly with Bitcoin, and Ethereum wants to prevent that. So they don't want to have GPUs, FPGAs, and ASIC. So they want to keep mining to GPUs. GPUs is okay. They want to keep Ethereum GPU. So why? How? It's because they made mining use a lot of data, and they forced the miner to access this large data set. So it's at the time of this drawing, it was 1 gigabyte. So the idea is that you have a header, right? And with the header, with the header of the past blocks, you can create a seed, and from that seed, you create a large data set, right? This DAG. So that data set is 1 gigabyte of memory, and now it's growing to 4 gigabytes. And it looks random, but it's actually coming from one single value, right? It just happens to be very large on purpose. And the idea is that if you want to provide a candidate, you are asked to provide part of that data set. So normally the hashing would be that you get the header, right, and then you suggest a nonce, and then you put these two together with a hashing function, and your output will be that thing here that you determine whether it's a success or a failure, right? Because it's lower than or greater than the threshold, than the difficulty threshold. But for the case of Ethereum, this Ethash algorithm, there's this whole part in the middle that involves looking at part of this large data set, right? And this is going to be picked in a non-predictable way, because you first hash something, and that first hashing gives you one index to look up. So you will see, okay, I need to look up that particular entry, and then that data has to be read, and mix it with the previous value that you got, and the result will tell you to go and look for another page, right? So that process here is, once you have the first step, you can't look ahead all these pages, right? And you can't save the memory, because even though you're gonna have to look at one page randomly, you don't know which page you're gonna which location you're gonna have to pick. So you obviously don't pick like the 2 GB of DAG, right? But you only pick you can't predict what you have to pick, right? And at the end, this whole mix, so you mix, and it will be the hash mix that will be included at the end in your block, right? So the verifier here, one of the stuff here is that the verification can be done, because this set here can be checked by using only a smaller portion of the DAG. Alright, so is it explained here? No, it's not explained in this view, but let's see. Okay, explained in this particular link here. Okay. So you have a seed, right? And then you can compute only 16 megabytes of data. And that data is random, pseudo-random. Right? I mean, it's as good as random for all care. It's not really random, because obviously it depends from the seed, right? And then from that cache, we generate this data set, which is a DAG. So they say 1 gig, but now it's 4 gig, right? And the 4 clients need to have that data set, because they're gonna be asked to look for pieces of that, right? And then these spatial elements will be put into the result, right? The beauty of the verification, right, is that for verification, you only need the 60 megabytes of data, because basically once you know where it is, you can take a shortcut and see how these particular pieces of the mix were using this random cache, this cache. So for example, you would say that you need to take entry 1 and entry 3 and mix them together, and then entry 2 and entry 4 you have to mix them together, right? And so something like that, right? But as your guy here, the miner, he cannot know in advance that it's gonna be these particular items that are going to be mixed. So he could mix them as it goes, right? But that would be super inefficient, right? So it's better for it to keep the large data set, the 4 gigabytes, even though it's going to be it's going to be only picked a few items out of it. And that size, 4 gigabytes, is chosen so that you can store this set in the memory of a video card. Right? It's still okay. So most video card would have more than 4 gig. I mean, not most, but many video cards will have more than 4 gigabytes of VRAM. But that's not something that you would have in a dedicated chip. Like ASIC would have only a few bytes, because ASIC is basically gonna only have storage for registers. So having to rely on this particular large data set prevents miners from using FGPA. FGPA are chips that can be hardware that can be reprogrammed, and then ASIC, which are even further. That is the last piece that we wanted to cover, because now we can go here and understand what is this mixed hash here. Right? So you have to provide the mixed hash to prove that you have done this particular work here, and then you have to provide the nonce. Right. Okay, that's, I think it's longer than I expected, but I think it should give you, I'll relate it to myself, I have a better understanding of all these data structures, even though, and this is helpful when you want to program in Ethereum, even if you're just a developer in Solidity, or even just a user of Ethereum. Knowing at least part of this is important, because for example, it gives you the distinction between different types of clients, and the things that you can do and cannot do with them, and how it affects your security. And with that, this concludes this series. We are going to resume with our liquidity pool project. So I thank you for staying and through this fairly long series. I hope it was useful.